This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today, we're delving into a research paper proposing a novel framework for transportation system modeling using large language models, LLMs, and LLM-based agents. The authors argue this approach can overcome limitations of existing agent-based models. What are the core limitations of current agent-based models in transportation system modeling that this paper addresses?
Current agent-based models often rely on simplified behavioral assumptions, like utility maximization, which don't fully capture the nuances of human decision-making. They also require extensive, high-quality data for calibration, limiting their applicability, especially in resource-constrained settings. Finally, evaluating alternative scenarios and policies often necessitates significant coding and model adjustments, hindering their use in practical planning.
So the LLM agent approach aims to address these limitations. How does the proposed framework leverage LLMs to improve behavioral realism?
LLMs, trained on massive text datasets, inherently capture a wide range of human language patterns and decision-making styles. This allows LLM agents to exhibit more realistic and nuanced behavior compared to models based on predefined rules or simplified utility functions. The inherent flexibility of LLMs allows for more realistic modeling of bounded rationality.
The paper mentions reducing data requirements. Can you elaborate on how LLMs contribute to this?
LLM's pre-training on vast datasets provides a rich foundation of knowledge about human behavior. This reduces the need for extensive, specific data collection for calibration. Furthermore, fine-tuning LM agents through natural language prompts allows for customization and adaptation to specific scenarios with minimal additional data.
The paper highlights improved support for alternative evaluation. How does the LLM agent framework facilitate this?
The flexibility of LLMs allows for easy customization of agent behavior through prompts. This eliminates the need for extensive coding changes when evaluating different scenarios or policies. LLMs can also reason about unfamiliar situations using their pre-trained knowledge, making the framework more adaptable.
The paper describes the system design. Can you outline the key components of the LM agent architecture?
The LLM agent architecture includes an LLM core for processing and generating language, a memory system, short-term and long-term, to store experiences, and an identity core defining the agent's socio-demographic characteristics and tasks. The agents interact with a dynamic transportation network simulator, perceiving the environment, reflecting on experiences, planning actions, processing plans, and executing actions.
The paper demonstrates behavioral tuning. How do the authors ensure the LLM agent's choices align with human travel behavior?
The authors employ several techniques. They use few-shot learning with historical data to align activity scheduling, destination choice, and mode choice behaviors. They also incorporate a reflection module to mimic human memory consolidation, focusing on key summaries and extreme events. Furthermore, they integrate concepts like bounded rationality and theory of mind into the agent's decision-making process through prompt engineering.
The bottleneck example is used to illustrate learning and adjustment. Can you describe the setup and the observed results?
The bottleneck example simulates a congested road segment. LLM agents, initially with random departure times, learn to optimize their departure times over repeated simulations to minimize travel time and arrival time costs. The results show agents adjusting their departure times over time, spreading out to reduce congestion and demonstrating learning and adaptation.
The paper acknowledges some technical challenges. What are the key limitations of the proposed framework?
One challenge is enhancing behavioral alignment, particularly in capturing the inherent randomness of human behavior. Another is scalability. Running large-scale simulations with many LLM agents is computationally expensive and time-consuming. Finally, rigorous verification of both individual agent behavior and system-wide simulation outcomes is crucial but challenging.
The paper suggests potential solutions to these challenges. Can you briefly mention some of them?
For behavioral alignment, exploring methods beyond temperature adjustments to introduce more randomness into LLM outputs is needed. For scalability, techniques like creating representative agents or using gradient-based methods could improve efficiency. For verification, more comprehensive validation against real-world data is essential.
What are the broader implications of this research for transportation planning and simulation?
This framework offers a potentially transformative approach to transportation modeling. By improving behavioral realism, reducing data needs, and simplifying scenario evaluation, it could significantly enhance the accuracy and applicability of agent-based models in real-world planning and policy analysis.
The authors mentioned several existing agent-based models like TRANSSIMS, MATSIM, Simobility, and Polaris. How does this proposed LLM agent-based framework compare to these existing models?
The key difference lies in the agent's decision-making mechanism. Existing models rely on predefined rules or econometric models based on behavioral assumptions. The LLM agent framework uses LLMs to generate more realistic and nuanced behavior, reducing the reliance on strong assumptions and allowing for more flexible adaptation to new scenarios.
The paper cites several studies on LLM agents in other domains. How does the application of LLM agents in transportation modeling differ from these other applications?
While other studies have explored LLM agents in games, social networks, and economic simulations, transportation modeling presents unique challenges. It involves a more complex, multi-layered decision-making process with indirect interactions between agents, requiring a more sophisticated agent design and system architecture.
In conclusion, what are the key takeaways from this research paper for experts in transportation modeling?
The LLM agent-based framework offers a promising new direction for transportation system modeling, addressing several limitations of existing approaches. While challenges remain in behavioral alignment, scalability, and verification, the potential benefits in realism, data efficiency, and scenario evaluation are significant and warrant further investigation. The framework's flexibility and adaptability to new scenarios and policies make it a compelling alternative for future research and practical applications.
Thank you for this insightful discussion.